Hello again. I'm Dag Ågren and I'm the staff engineer for iOS here at Wolt. I was basically the second ever iOS developer at Wolt, so I've been here for ages. So if afterwards you have any questions or want to learn about how we do iOS things here at Wolt, then feel free to come and talk to me. But for now, what I'm going to do is I'm going to have this presentation, as you can see here. Now this, I'm guessing you might already have some questions here, such as, what is the diamond problem? Which might not be clear. So the diamond problem that we're dealing with here is this. That's the diamond problem. Basically, you have a graph that splits into two nodes and then joins back into one node. This is a problem. So basically, it's a problem in various places. One obvious one where you mostly hear this mentioned is in multiple inheritance in programming languages. And well, these days, languages with multiple inheritance is pretty much C++, so nobody here probably cares about that. The idea is that you can have like a class that inherits from two other classes that inherit from the same class, and then you run into all kinds of issues. So that's the diamond problem in that context. What I'm going to talk about is the diamond problem in reactive graphs, which is probably something that people here are more familiar with. There's probably diamond problems in other contexts as well, but I don't really know about them. So reactive graphs is what we're talking about here. Now, so what actually is this? How does this actually look? Now this presentation now is, I'm an iOS developer, so this is going to be about combine in Swift. But most of this presentation applies equally to any like reactive framework like RX, Reactive Swift, or whatever it is Kotlin people use. I hear there's another one there as well. But basically you have reactive streams of values over time, basically. Hopefully people are familiar with that, otherwise this will be very confusing. So here's an example of some code you might want to write. This is very simplified and very stupid, but it shows the problem of the exact same graph we saw earlier. So what we do is, here we have A, which is a pass-through subject. That's just like a thing that can publish new values. And then we take that stream and we do two maps. We do one in them is we multiply the number that comes through by 2, and the other one we multiply by -2. So that's very simple. And then for the last step, we do a combine latest operator. So we take the values from both of those and we combine them together with a map where we just add them together. Now, this is obviously very trivial, but like what you would expect here is that if you put in the value 1, the B and C would go to 2 and -2, and you combine them together, it should be 0. So you should always accept B to contain 0. No, D to contain 0. So there's a little bit of code that just prints out whatever values come through D, and then we try to send a couple of values. So what happens? Well, this is the output we get. The first one is obvious. We send a 1 and D is 0. That's fine. Then we send a 2. Now D is suddenly -2 and then D is 0. And that's not really what we expected here, because like a value plus minus the same value should be 0. So same thing happens when we send a 3. So what is really going on here? So we try to change the code a bit to debug it a little bit to see what exactly is it that we're adding together. We just add a bit more to the print statement to print out the actual individual values. Now what we get is, okay, the first case, 2 plus -2 is 0, fine. Then we get 4 plus -2 equals 2. And interestingly, also it's not -2 anymore, now it's 2. And then we get back to 4 plus -4 is 0, and then similarly for the next one. So we want to look a little bit closer at what is actually going on. So we had even more print statements because we're doing print debugging here. So for each of the B and C, when we map the value, we print out what value we actually have. And what we get is, in the first case, it's obvious, like B becomes 2, C, which, oh, I noticed I have a little typo. That should be C is -2. And then we add them together, it's 0. In the other case, B goes to 4. And then suddenly we calculate 4 plus -2 equals 2. That's not what we wanted. And then we set C, again, misspelled there, to -4, and then we get the correct value. And then the same thing happens again. So to demonstrate in bit more detail here what's actually going on, we can go back to our graph. This is what we still have with our A, B, and C and D things. So what is actually happening when we start running this code is that we emit a value of 1 from A. A will now have to go and inform its children of what value it got. So it sends the 1 to B, and B calculates, oh, 1 times 2 is 2. And B will then send this onwards down towards D. Now D is special here because it doesn't have any input from its other branch, so it doesn't do anything. It just remembers, okay, there was a 2. So A goes on to send it to its next child, which is C. And C calculates, oh, that's -2, and sends it on to D. Now D has both values, and it can finally calculate the value, and it's 0, and it emits that. And this is what we expect to happen. This is all perfectly fine. So A is now finished, and this is what we're stuck with. So now we send a 2. And A does the same thing. It sends it here. B calculates it's 4, and sends it onwards. But D is still remembering the -2 from before. So now it's calculating the sum of the new value and an old value, which this isn't what we want at all, and not really what we expected. And now we have this incorrect value, which is then immediately emitted, and we have the wrong thing. And then we send it to the other one, we calculate -4, we send -4, and now we're back to what we expected, a 0. So this is a bit ugly. Now this is obviously, this is a very simple example, but at least, I don't know about you, but at least at Wolt, like, we do get these problems when you do a lot of reactive programming. Like, because you often have, like, you receive some data over the network, which contains all kinds of values. You might use a map to split that out into individual values that you pick out of that object. And then somewhere far down in your logic, you happen to take those streams and you go, oh, I need this and I need this. I will just combine them together. And suddenly you're getting weird updates in your code where you're outputting inconsistent values and your values are flickering back and forth, and it's generally unpleasant. So, and another thing is this could be much worse than that. Like, you can have some kind of graph that looks like this, and like, God knows what happens if you put a value in at the top there, like how many values you're gonna get out at the bottom. Let's not go into that right now. So the big question is, what can we do to fix this? Now, what people tend to do in this case is they add a debounce somewhere because you're getting too many values, so you debounce it with a small timer. But that's kind of that doesn't feel good as a solution. Like, you might be filtering out things that were meant to come through, and you're adding some weird latencies into your streams, and it's generally not nice. So is there a better solution we can do? So basically, we're looking at our graph again here. So what we can do is this is what we've tried to do now as an experiment here at Wolt, and is that we could add some new operators to our reactive graph here. So we can build something that looks like this instead for the very simple example. We've added a couple of, see. So we've added what I called a gate. So what it does is it detects that there is something in an incoming value, and it sort of initiates this whole process. And then we have a debounce operator that basically works so that once the gate has triggered, it will start blocking values from coming through, and it will wait until then. Yeah, so how does that work in practice then? So the gate creates this queue of updates, and like to initialize this whole process. And then the debounce checks that when it receives a value, is there an active queue started by the gate? That's sort of the stop signal that we have this queue in place. And if we have one, instead of sending the value onwards, it will just register a callback in the queue that will send a value onwards, but it won't happen yet. And so once the control flow, like as in the earlier case, once the gate has finished sending its data on towards everything, and like we have finished and we're back and executing code at the gate again, then it will go through the queue and it will call each callback there so that the debounces will finally send their values onwards. And another trick here is that the debounce will send the latest value it received. So like if it got multiple values, it will ignore all the early ones and just send the latest one when it's finally done. And then the gate will remove the queue because we're done. So to show an example of how that works, we can do another one of our little animations here. We're now in the same state as like halfway through the previous example. We already sent the 1 through because that worked fine. So now we still have the 2 and -2, remember, then we start sending a 2 through here. So the 2 arrives at the gate, and the gate now activates and stops things. And then it starts just forwarding the event. So it goes here as before, calculate a 4. The 4 gets sent down here, and now we get the incorrect value. And that gets passed on down to the debounce. But the debounce now is stopped, and it just stores the value and doesn't send it onwards. And the gate sends the value to the C here and gets a -4. The -4 gets forwarded. Now we get the correct value 0. That is sent to the debounce, which still doesn't do anything. It just stores the 0 and forgets the old one, which was wrong. And now the gate is done, so program control has gone back to the gate, and it stops what it's doing, it stops blocking things, and now it triggers the callback that the debounce had, and the debounce will now send the value onwards. And now we just have 2 zeros, as we expected. We got rid of our extra values that we didn't like, and that were completely wrong. So, is it really that easy to solve this? Well, no. I thought it was this easy when I started this project, and this is a bit of a case of we do these things not because they're easy, but because we thought they would be easy. So one thing now is, okay, this queue is a little bit weird. It has to be sort of global state, but if you're in multi-threading thing, it has to be thread local, so that you have one of these queues per thread in case you have multiple things happening on multiple threads. You don't want to mix up the queues, but it's still sort of a global state for the whole thing. So hopefully the language you're using supports thread local things. Swift does with a little bit of hacking. So it worked fine in this case. And on the other hand, if like one of these operators starts jumping threads or introducing delays or things, then this whole thing breaks down and it's not going to work anymore, because the whole thing kind of relies on that all the processing happens when you send the value, not slightly later. But usually that's fine. You probably know when this is safe or not. But remember this. This is the second problem. We have something more complicated. So here we're going to need a lot of these debounces. So it might look something like this. We have just the one gate at the start, but then we have debounces after all of these combinings. I think I even forgot to add one after the D there. That should have been one as well. So yeah, this is getting a bit complicated. So once this has triggered, we have obviously a lot of stuff in the queue. The question is, in what order do we run the things in the queue now? And after some testing, I realized that if you just run them in the same order that they were registered, then this isn't going to work. Like this specific example is what I was testing with, and it still gets glitchy if you do it this way, because you get things triggered in the wrong orders. It is slightly better than before, but you still get garbage through. So what can we do instead? It turns out that what we really want is that we want them to run in dependency order. That is, we want the ones sort of higher up in the graph to run before the ones lower down. So like if one of them is depending on other ones, then they should run first. And this is annoyingly hard to figure out with the normal reactive APIs and things. Like how do you find out which other things you are depending on? So the workaround here was that instead, when we create these debounce gates, we just give them sort of an age, and then we run the queue in the order of like how old are these debounces, because that tends to be the same as the order in the graph. Like you tend to create the ones high up first and then the other ones later, unless you're being awkward and creating them beforehand and then putting them in later, which the workaround for that is just don't do that. It's weird. So if in this case, like you would number them like 1, 2, 3, 4, 5, 6, 7 going sort of downwards, and then you would just sort the queue by that number and run them in that order, and then it works. Then it actually works. Another problem is that you might end up with multiple of these gates. Like if you have big, complicated program logic, then maybe one part of your logic includes a gate and debounce, another part also has them. So you might have multiple gates, but it turns out that that's quite easy to handle, because the gate can just check that, okay, has another gate triggered already? If so, just do nothing, leave it to the earlier one, and then everything works fine. So we have a library called Diamond Debounce that we made for this. And I have a quick example of how our example would look if we use that. So we go back to the code we had before, which is this one with our debugging here. And here we now try to add the helpers from this library. So what it looks like is that we create an A2 there, which just adds a diamond debounce gate. And then after the combine latest, we add a diamond debounce. And then we run it. And the output is perfect. We'd only get zeros output, everything works fine. So from the point of view of the code actually using this, it's very simple. We also added like some helpers so that you don't have to do a combine latest and diamond debounce. Like we just smash them into one, like debounced combine latest or whatever, to make it very easy to do all of this work. So if you want this code, then it is actually released. You can get it from here. This is obviously only for combine. So if you're using Swift, you can try this out. It's very much in a beta state for now. I only released it a couple of hours before this presentation. So there is documentation in the code. I just haven't generated any of it for the site. So it's a bit in a rough state. Hopefully it will get better soon. But you can try it out if you're curious. And it would also be interesting to see this, like obviously all of this applies to all of these frameworks. Like you could do this in RX Java, or RX in JS or whatever. So it would be interesting seeing if this could be ported to other systems. Like I'm not going to do it because I don't really care about those, but I assume there's other people who care about them. So that might be interesting to experiment with implementing the same thing there. But yes, that is about everything.